Welcome to Ready to Derive. In the last video, we learned how to determine limits using algebraic methods such as simplifying, factoring, and rationalizing. However, there are some functions that cannot be algebraically manipulated to the point where we could use direct substitution, and so we need another tool in our kit. In this lesson, we will acquaint ourselves with the Squeeze Theorem, which, although somewhat limited in its application, provides a really cool way to determine the limits of some otherwise elusive functions. As always, there will be lots of practice problems and accompanying visuals to keep it real. Without further ado, let's get started. So let's get straight into the statement of the Squeeze theorem. And there's some preconditions here. So if we have three functions, f, g, and h, structured in this way, that where sort of g is bounded below by the function f and above by the function h, when x is near a particular value a, so g potentially could be undefined at a, but this theorem would still apply. So let's make a picture of this before we get into the statement of the theorem. So here's h hovering over here. This has to stay strictly above g. And here's f. So part of the preconditions for this is, for the Squeeze theorem to apply, is that f and h are in fact going to have to meet at some point, otherwise the Squeeze theorem wouldn't apply. And here we have g. G has to stay between the two functions, at least near a, has to stay between the two functions, and the only way it can stay between the two functions is if it gets pinched or squeezed at this particular, or at a particular value of x. Let's call that a. So if this is all true when x is near a, and then another condition, and if we know that because h and f have sort of touched together at the point x equals a, and let's say, so if they're touching together here, and the limit here is L, and remember, I mean, even f and h don't have to be necessarily defined at a, but their limits can still exist. So if this is all true, a lot going on here, then we can conclude something that's probably very obvious from the picture, is that the limit of the green function, g of x, let me just label this, as x approaches a, g of x has no choice but to share the same limit as h and f. So let's get straight into the use of the Squeeze theorem with an example. So here's a function, x squared cosine 1 over x squared, which we can't, okay, so if you try and plug x equals 0 in, clearly we're okay plugging in for x squared, but this is going to be, this expression here is going to be problematic. 1 over 0 does not exist, and so we can't rely on direct substitution. And I hope you can also see that there's no algebraic methods we could apply. We can't factor, we can't rationalize, we can't simplify fractions. So this is where the Squeeze theorem comes in handy. And it's the most important thing is finding a function or two functions between which this function is hemmed in. And so that comes into employing what we know about cosine, that the cosine or sine of any quantity has to lie between 1 and -1. It may not exist. I mean, this is not true because it's undefined at 0, but we have in fact identified two functions, they're y equals 1 and y equals -1, between which cosine of 1 over x squared is always hemmed. And so the next step then becomes just to, since we want x squared in the expression, just to multiply throughout by x squared. So we get that this is less than or equal to x squared, and that it's also greater than or equal to -x squared. And so now all we have to do, we have one of the preconditions of the Squeeze theorem, and then we have to actually sort of find out what happens when we plug x equals 0 into the upper and lower functions. So if we plug 0 into here, the left side function, we get 0, and in the right side, so x squared, we also get to 0. And because those two limits exist and are equal to one another, so they're both equal to 0, that implies that, in fact, the limit of x squared cosine 1 over x squared as x goes to 0 by the squeeze theorem must follow suit and must actually match these two limits. So in the previous slide, we just established this limit using the squeeze theorem, and I thought a visual graphical representation would help. So here's a Desmos graph to make you sort of appreciate why it's called the squeeze theorem. The green function seems to be squeezed in between the red, the upper function, which is y equals x squared, and the squeezed in between y equals x squared and the lower function, y equals negative x squared. So sometimes I might use the term bounded by, so the green function is bounded on the above by y equals x squared and below by y equals negative x squared, or sometimes hemmed in between the two. This squeeze theorem is also known as the sandwich theorem, and for obvious reason, it's sort of sandwiched in there. So, and if you focus in on around x equals 0, you see that that's y equals x squared and y equals negative x squared come together right at x equals 0. And their limits, of course, are 0 at x equals 0. And so the green function, hemmed in between the two, has to follow suit. And that's why the limit of x squared cosine 1 over x squared has to equal 0 also. So let's look at another example where we can apply the squeeze theorem. Notice this function shares some similar attributes to the previous function, and that it's got its sine this time where it was cosine before, and we have the x squared there as well. Always try direct substitution first. Notice that x equals 0, you can't plug in because this is dne. All right, so since we can't do that, we can't do any algebraic manipulations, let's go and see if we can employ the squeeze theorem. So we know this is true. Sine will always be between -1 and 1, and of course this is not true at x equals 0 because sine of 1 over x is undefined there. Now the thing is, we're not ready yet to multiply by x squared because we need to sort of establish if this e to the sine of 1 over x can be hemmed in between two functions. Now, and luckily it can. Luckily we can raise e to the 1 on this side, e to the -1 on this side, and maintain the inequality. And that is only because e is a strictly increasing function, which means that, you know, if you have an input a that's less than b, then you know that e to the a must be below e to the b. So this would not be true if the function was oscillating or decreasing, but luckily with e this is true. And we see that this is the same as 1 over e. So at this point we can multiply by x squared, and we get x squared e to the sine 1 over x is less than or equal to e x squared, and is greater than or equal to x squared over e. And we're interested in the limit as x goes to 0. So let's look at the lower and upper functions. So the limit as x goes to 0 of x squared over e equals 0. And conveniently, the limit as x goes to 0 of e x squared equals 0. So it must follow that the limit of x squared e to the sine 1 over x by the squeeze theorem, being hemmed in between these two functions, must also equal 0. Sorry, I forgot this here. So the limit we just established in the previous slide using the squeeze theorem, let's take a look at the graph of this on Desmos because it's so pretty to look at. And in the green function, as we can see, is bounded from above by y equals x squared e, if you recall, and from below by y equals x squared over e. So it just sort of oscillates back and forth between those two functions. And we can see if we hone in around x equals 0, that that's at x equals 0 is where the orange graph and the purple graph come together at 0, and so the green function has no choice but also to adopt the same limit. So as x goes to 0, the limit is in fact 0. So let's look at a scenario when x tends to something other than 0, just to change it up a bit. So we're going to find, if we can, the limit as x goes to infinity of this expression. And by now we're getting pretty confident in the way we start off with these type of problems. Once again, recognizing that cosine, the value of cosine must be between -1 and 1. And now we sort of algebraically have to construct the function that we see above. So let's multiply throughout by -1. So if we, to get negative cosine x, to multiply by -1, you do have to reverse the inequalities. So you would get that inequality. And just to put it from, arrange them from smallest to largest, let's just rearrange that to something we're more familiar with. And here we go. So now we have negative cosine x, but we need a 1 in front of there. So let's add 1 throughout. So if we add 1 to everything there, so let's just add 1 throughout, this will become 0 is less than or equal to 1 minus cosine x is less than or equal to 2. Now all we're missing is that denominator of x plus 2, in which case we could literally just divide through by x plus 2. So 0 over x plus 2, well, we know that's just 0. And we could put this over x plus 2 and the 2 over x plus 2. Now, sometimes the squeeze theorem is formulated sort of like slightly differently. In other words, if we know that this function is hemmed in between 0 and 2 over x plus 2, then we know that the limit as x goes to infinity of 0 will have to be less than or equal to the limit as x goes, oops, sorry, that was infinity, as x goes to infinity of this quantity over x plus 2, which has to be less than or equal to the limit as x goes to infinity of 2 over x plus 2. So this is kind of the squeeze theorem in a slightly more efficient, condensed manner. Now, if we know that the limit of 0 as x goes to infinity is just 0. And we know as x goes to infinity here, we'll have 2 over a very large number, which is also therefore equal to 0. And that leaves us no choice, or leaves the middle function no choice, but to follow suit, so that the limit of 1 minus cosine x over x plus 2 as x goes to infinity is equal to 0 also. So we just established this limit in the previous slide, and we'll look at this graphically again. So our green function is nicely hemmed in from above by y equals 2 over x plus 2, and from below by y equals 0, which is nice, a constant function. If you can get your upper or lower bound to be a constant function, it certainly makes for easy algebra. And you can see that as x goes to infinity, the y equals 2 over x plus 2 is approaching y equals 0, and therefore forcing the green function to follow along. So a note of caution when working with the squeeze theorem and manipulating inequalities. As you know, you have to be careful that you're not dividing by or multiplying by a negative number. And in the previous problem we did, you might have wondered about that when I divided by x plus 2, but since x was going to infinity, it didn't matter. But let's look at this example. And let's start off as we always do with sine of 1 over x. We know that it's between -1 and 1. And we might be tempted, without thinking, just to multiply through by x and apply the squeeze theorem and work out that the limit of x sine 1 over x is 0 just by plugging in. But this inequality is only true, this one here is only true if x is positive. If x is negative, and we were to multiply the starting inequality, so if we were to take this and multiply x by x when x is negative, we would have to reverse the inequality. So we would end up with this. Now, which is fine, because in fact we can establish from limits from the right and from the left. So I'm going to leave out a few steps here and just say that the squeeze theorem could help us to decide that, or to find that the limit as x approaches 0 from the right of x sine 1 over x is equal to 0. And again, the squeeze theorem applied to this inequality would establish that the limit as x approaches 0 from the left of x sine 1 over x is equal to 0. And because the left and right limits exist and are equal to one another, we could conclude, therefore, that the limit of this function is indeed 0. So in the previous slide, we established this limit using left and right hand limits. And here's a beautiful picture to show how the upper and lower bounds, if we remember, so this is y equals x. Y equals x was the upper bound for the green function when x is greater than 0, but notice it switched and became the lower bound for when x was less than 0, and vice versa. Y equals negative x was the lower bound, and then switched, and y equals negative x became the upper bound. So just something to be aware of. More often than not, we're multiplying by x squared, etc. As long as you're multiplying by a positive number, you're safe. But if you end up multiplying an inequality by x or x cubed, you do have to be a little careful. So we're going to end with one sort of variation on a squeeze theorem problem that you might come across in your studies. So here you are told that the function g of x is bounded as follows. We don't know what the actual equation of g of x is, but we have enough information. We know between the two functions between which it's bounded. And the question is, can the squeeze theorem be used to determine the limit as x goes to 0 of g of x? Well, if we know the functions are orchestrated in this manner, then we know that this would be true, in fact. So if we took this limit of the lower function, whatever that limit is as x goes to 0, we know that it will be less than or equal to the limit of g of x as x goes to 0, etc. x plus 1. That's going to be less than or equal to the limit of x plus 1. And then all that's left is to, by direct substitution, actually evaluate these limits. So if I plug in 0, I get 0 times pi is 0, sine of 0 is 0, and the final answer is 0. But on this side, if I plug in 0, I get 0 plus 1, which comes out to be 1. So because those limits don't match, I don't know, I can't definitively say what the limit of g of x as x goes to 0 is. I do know that it lies in this range. So it is certainly going to be somewhere between 0 and 1, but I can't pin it down with any accuracy. So this begs the question as to whether we could find the limit of g of x as x tends to any other values. Obviously 0, the limit as x goes to 0, we couldn't find that out, but I'm telling you that there are some values for which it's true, so let's go find them. So to save a little time in this video, which is getting very long, here is, I've just typed these out. So here is our function bounded in this way by the squeeze theorem. Well, actually not by the squeeze theorem just yet, but we can be sure that the limits would also be bounded in that way. And what really matters here, of course, if we want to be able to apply the squeeze theorem, this has to equal that. So that's what I've just extracted out in the next step. And I plug in, I replace x with a throughout, so direct substitution. And I subtract a from both sides, and I get sine pi of a equals 1. Now, clearly there are a lot of values for a for which that would be true. So if we go to this position P, we know that any rotation that lands us at P would indeed have a sine of 1. So there are a lot that would work. So we know that, for example, pi over 2 would get us there. 5 pi over 2, etc. And all the, some negative counterparts. But since I only asked for 2 values, let's just focus on these ones. And if I divide through by pi, then when a is a half or a is 5 halves, I have 2 values for which I think we can work out the limit of g of x. So let's end with the visual. Here is g of x and the way in which it's bounded again. So here we have the 2 functions. So this is y equals x plus 1, the upper function, and this is y equals x plus sine pi x. And we don't know what g it does exactly, but we do know that it's kind of bounded between here and here. So every once in a while, it has to kind of converge with the other 2. So, and as we could see here, at this point here, when x was 0, we just didn't know. We know that the function could be anywhere between 0 and 1, the green function, but we couldn't pin it down exactly. But if we look here at, this is a half, and also here at 2.5, we do in fact know the limits. So this is 2.5. So we'll just end with, we won't do both, but we'll just do one. So if we wanted the limit as x goes to 0.5 of g of x, well, we could read it off here. Looks like it's 1.5. Or you could just plug it in. So you could do the limit as x. You could plug into either of the functions because you know they meet there. So the limit as x goes to 0.5 of x plus 1, just plug it in. And that confirms the answer is 1.5. And that brings us to the end of this lesson. I hope you found it helpful. And if you did, please do click like and/or subscribe to my YouTube channel, Ready to Derive. Thank you.